In this video, we'll discuss acid-base titrations. An acid-base titration is an experiment that we usually perform in chemistry to find the concentration or molarity of an unknown acid or base. So we will utilize a neutralization reaction, but we will very carefully control it so we can collect data to determine this unknown concentration. The type of titration we will be doing is where we do not know the molarity or concentration of the base. So we would need to know the concentration of the acid, and we're also going to use what's called an acid-base indicator. This is a substance that we add in our titration, and it changes color when the pH changes. That's how we know to stop our titration. There are many choices for acid-base indicators shown in the table below. Since we are going to utilize a strong acid, strong base neutralization reaction, we want to look for an indicator that changes color somewhere in the neutral range. The particular acid-base indicator that we will be using is called phenolphthalein, and its two colors are colorless and pink. Here is a typical titration setup. We are finally going to use the burettes, and in the burette, what we are going to do is put the base, and this is the thing we are going to try to find the molarity for, or the concentration for. In the flask, we put the acid, and remember we need to know its concentration. And then also in the flask, we're going to put our acid-base indicator. And this diagram shows the phenolphthalein that is in the pink form. On the right is a photo of the actual burette and Erlenmeyer flask setup. In the photo here on the left, you can see the indicator being added to the acid that is in the flask, and the base is in the burette. In the middle photo, they are carefully adding the base to the acid. You can see it start to turn pink. And then on the photo on the right, we've added enough base to neutralize all the acid in the flask. We have a slight pH change, and then the acid-base indicator changes color. It goes from colorless on the left to pink on the right. When we have added enough base to neutralize all of the acid, we reach what's called the equivalence point. Specifically, we have equal amounts of hydrogen ion from our strong acid and hydroxide ion from our strong base. So we would say the moles of hydrogen ion and hydroxide ion are equal. However, we can't see that. What we can see is the indicator change color, and it changes color at what we call the end point. So that's the end of the titration. So if you add just a tiny bit more base after you have neutralized all of your acid, you get the pH to change and the indicator changes color. That's how you know to end or stop your titration. Experimentally, the difference between the equivalence point and the end point should really be about 1 drop of your base, so they are close enough to be considered the same. At the equivalence point, we've added enough base to neutralize all the acid, or we have equal moles of hydrogen ion and hydroxide ion. So if we think about our molarity equation and the molarity of the acid, it would be equal to the moles of the acid per liter of acidic solution. Same for the base. The molarity of the base is equal to the moles of the base per liter of basic solution. At the equivalence point, your moles are equal to each other. So I rearrange the equation and set it equal to N, our moles. So we have our moles of our acid that are equal to the molarity of the acid times the volume of the acid. And then we have the moles of our base that are equal to the molarity of the base times the volume of the base. And those moles should be equal at the equivalence point. So we can derive a little equation to help us determine our unknown concentration of acid or base for a titration. MAVA equals MBVB. If you know the molarity and volume of the acid that you used in the titration, and you are able to measure using the burette the volume of the base that you added to neutralize the acid, then you can solve for your unknown concentration or molarity of your base, and that's what we will be doing in our lab. So let's do a little bit of practice. First, we're going to write the balanced chemical equation for the reaction between potassium hydroxide and nitric acid. We have a strong base and a strong acid. We said that when we have a reaction between a strong base and a strong acid, we're always going to get water and a salt, an ionic compound. So remember, we'll do our double replacement. I swapped out the potassium ion and the hydrogen ion, and instead of HOH, I wrote H2O, and potassium nitrate then is KNO3. Potassium has a +1 charge, and nitrate has a -1 charge. Our water is always going to be in liquid form, and our salt should always be soluble in water, so we'll label it as AQ. It'll make an aqueous solution. So this is our reaction for our titration, and in number 2, it says that we used 0.35 molar of the nitric acid. It was 56 milliliters, and we needed 25 milliliters of the potassium hydroxide to neutralize that, so we could find the unknown concentration of our potassium hydroxide. So we will use this equation. The molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base, because the moles of acid and base should be equal at the end of this titration. I plug in for the molarity and volume of the acid, 0.35 molar and 56 milliliters. And then the molarity of my base is unknown, but I know I needed 25 milliliters of potassium hydroxide to neutralize my acid. So I'm going to solve for the molarity of the base. The molarity of my base is 0.78 molar. Don't forget units on there. And I'm doing 2 sig figs since all of the numbers have 2 sig figs. There are 3 remaining questions in your notes. Please complete those now and then check your answers with the answer key on Canvas.